Hello everyone, this is Mark and welcome to the second episode of the Death by Variance video series. So in this episode, we're going to talk about probability in MTG, the hypergeometric distribution, IIDs, and U. So first of all, let's talk about the term random. And let's discuss what is this term? What does it mean when you say that something is random? So random is a characteristic of an action or an experiment. So when something happens, we can consider that something as either random or deterministic. So when we say that something is random, it means simply that it's not deterministic and vice versa. So what do we mean by random? Random means that the outcome cannot be predicted with 100% accuracy. Okay, so that's what we mean by the term random. And so we have a few examples here of what we know as random events. So for example, when you toss a coin. When you toss a coin, you don't know if it's going to come up heads or tails, and thus it is random. On the other hand, if you are tossing a two-faced coin, then that means that you know the outcome every time you toss the coin. And so it is not random in that sense, it's deterministic, because every time you toss it, you know that it can only come out heads, because both of the sides of the coins are heads. So on the other hand, if you're rolling dice, then that is also random, right? Because every time you roll the dice, you don't know what's going to come up. However, if you have loaded the dice, so that they will always come out as sixes, then that is also no longer random, that is deterministic. Of course, if you load the die so that it will only come up 6 um, more than 20% of the time, but not all the time, then that is still random. Although now there is no longer an equal chance of each of those outcomes from appearing, because 6 will appear more often than the other numbers. Still, with every throw of the dice, you do not have a way of knowing with 100% accuracy what's going to be the outcome. And so that example remains random rather than deterministic. So even the third example that we have here, which is essentially meant to represent the time it takes for you to travel from your home to your work. So that is also random, because every time you do that event, every time you travel, it's different. Sometimes it may be the same, so it may take you 15 minutes today and it may take you 15 minutes tomorrow, but it's unlikely. Maybe it takes you 15.333 minutes today, and tomorrow it takes you 15.00003 minutes. So those are two different numbers. And so it remains random. So, however, while random means that any one outcome is not predictable. When you toss a coin, you cannot predict how it's going to land. If you throw a die, you cannot predict how it's going to land with 100% accuracy. It does not mean that the behavior of something random is indescribable. That means it doesn't mean that something is random, that we cannot understand that phenomenon better. It is describable. When you have something that is random, it is possible for you to describe how that variable behaves. And that behavior, describing that behavior, the description rather of that behavior is referred to as that variable's distribution. Thus, for many actions that are random, for many variables that are random, it is actually very possible to know what the distribution is. Specifically, for drawing cards from a well-shuffled deck, okay, for drawing cards in a well-shuffled deck and counting the number of a certain type of cards out of that deck. For example, counting the number of hearts cards that you get from drawing a 5-card hand. Okay, so that distribution is known. Okay, and that is referred to as a hypergeometric distribution. Okay, so formally, a hypergeometric distribution is a distribution of the number of X-type cards out of N cards drawn from a deck containing big N cards, small m of which are of X type. Okay, so an example of that, and the one that we the one that we did an experiment on in this episode, with your help, with the viewers' help, with the help of people who have contributed data from their own play experiences. Thank you very much for that. Is the number of lands that you draw in an opening hand of 7 cards from a deck of 60 cards and exactly 24 lands. Okay, so that is a hypergeometric distribution where your big N is equal to 60. So this is your big N. This is your big N. Your M, little m, is 24, and your small n is 7. And so if you know those 3 numbers, then you can plug them in this equation that you see here. Okay? And that will give you the probability of getting each, or the probability of getting each of the possible number of outcomes when you draw 7 cards. Okay? So what are the possible outcomes? It's possible for you to get 0 lands in your opening hand. It's possible for you to get 1 land in your opening hand, 2, 3, 4, 5, 6, up to 7. So those are the 8 possibilities that you can have every time you draw a hand of 7 cards. Okay, and you can compute each of those probabilities by using that formula, because that random variable counting the number of lands in your opening hand is governed by the hypergeometric distribution. So what do these distributions look like? So here are some examples. So if you're tossing a coin, so there's an equal, so assuming that the coin is fair, there's an equal chance of it coming up as heads or tails. So when you toss it over and over again, you'll get something like this. Half of the time it's going to come up as heads, the other half is going to come up as tails. For tossing a fair die, so it's similar. So each outcome has a probability of 1/6 of occurring, and therefore if you toss the die over and over again, you will get a distribution like this one. Okay. Now on the other hand, if you draw a hand of 7 cards over and over again, so from your deck of 60 cards where 24 are lands, so if you shuffle properly and then draw 7 cards, then shuffle again, shuffle your entire library again, then draw 7 cards, and so on and so forth, it's going to look like that. Okay, so you will get mostly 3 land or 2 land hands. To a lesser degree, you will get 4 land hands. You will rarely get no land hands, but the rarest that you're going to get is 7 land hands. Even a 6 land hand is more rare than a 0 land hand. Okay, so that's the distribution that you're going to get, or that's a distribution that you're going to get whenever you repeat the experiment of drawing 7 cards from a deck of 60 cards with 24 lands. Now we know what we mean by a hypergeometric distribution. Let's talk about what we mean by IID. So IID stands for Independent, Identically Distributed. So there are 2 important terms here, independent and identically distributed. So what do we mean by identical? Identical simply means that the same mechanism is being used to generate the outcome. So that's why in our experiment, I asked you to um, provide data from doing best of three. So it doesn't matter if you were doing historic or you were doing standard, as long as you were doing best of three, you are using the same shuffler. So every one of us who does a best of three ranked match is using the same shuffler. And so it's identical. The shuffler that you're using in your match is the same shuffler that I'm using in my match. Second is independent. So what does independent mean? It simply means that the probability of each outcome is unaffected by any previous outcome. So that means that when you draw your seven card hand, and you see that you have one land in that hand, that does not affect whether or not you will get more lands in your next seven card hand. It doesn't affect that. So you can still get a hand with one land the next game. That's very possible. It's not likely. I mean, the probability is small to get one land in the first place, but it's possible. And it is not affected by the fact that you already did it the previous game, the previous match. Right? Also, your experience is independent of my experience. If you get a hand with one land, that does not affect how many lands I would get when I play my next game. So what is the consequence of us being able to assume that indeed our experience with the shuffler is IID? Right? That is that we are each using the same shuffler and we are doing so independently. So what that does is it allows us to combine our experiences with the shuffler under the same condition. That is under best of three, where we can establish that we are using the same shuffler. And if we do that, we should be able to anticipate the distribution that will form. So we know that distribution, right? We know that that distribution should be hypergeometric. So it should be hypergeometric with those parameters. That is, we are drawing 7 cards. You are drawing it from a 60 card deck with 24 lands. And your variable of interest is the number of lands that you draw. More importantly, now that we know what to expect, then we can check if the resulting distribution that we get from combining our experiences differs significantly from the one that we anticipate. Okay, so now that we've gotten all the theory out of the way, let's see the concepts that we talked about in practice. So first, let me present to you the data that we were able to gather. So thank you for all the contributions of your data. We were able to gather a total of 141 matches. Okay, so we were able to gather, not matches, sorry, 141 games. Okay, so 141 games in all from, I think, let me check, 19 respondents. So we had 19 respondents, and in total we were able to gather data from 141 matches. So, no, again, 141 games. So I have stored those in this variable so you can see. So those are the total data points that we were able to collect. Now, like I said before, the behavior of the variable of interest that we have is hypergeometric. With the parameters 24 lands, 60 card deck, and a hand of 7 cards. So this software R is actually capable of producing random numbers from that distribution. Okay, so I've coded a lot of stuff here. So this is how you can get a sample of numbers from that distribution. So here, I want to generate a sample of 5 numbers from that distribution. That's why you see 5 here. Okay, and the rest are the parameters of that distribution. So when I press enter, you will see a sample of 5 cards I mean not 5 cards, 5 hands drawn from that distribution. So if we translate it to, if we translate this simulated um, data to our context, so it means that uh, we had 4 lands in the first draw, 3 lands in the second draw, in the second hand, 4 lands in the third, 3 lands in the fourth, and then 2 in the fifth. Okay, so we can do that again, and we will get a different outcome every time. Okay. And so actually, we can simulate the entire experiment that we were doing. So instead of the data, instead of our raw data, we can simulate data from the actual distribution that we're expecting and see the behavior of uh, that distribution. So I have some code here that I'm going to show you. So in this code, I will generate data from the hypergeometric distribution with the necessary parameters, 5 at a time. And then I will add them together. So each time, the data set is going to become larger. So this is similar to what we actually did, where we had players who are contributing data, and then another player contributes data, and so on and so forth, and the data set becomes larger and larger. So this is similar to that, except that instead of just 141 data points, we are going to go for about 2,000 data points. And you will see what I mean by the distribution becoming closer and closer to the distribution that we are expecting, if indeed the elements are being drawn from the correct distribution. Okay, so remember what the hypergeometric distribution looked like in the previous slide, right? So here's the code. We're going to see it now. Okay, so as you can see here, um, we are adding more and more data, right? So as you add more and more data, the distribution becomes closer to that hypergeometric distribution. And it comes to a point where adding more data no longer changes the distribution. Okay, so it's, as you can see here, it's no longer, it's still adding more data, it's still moving, but it's no longer changing the distribution. So now it stopped. So we already have 2,000 worth of data that you see there. And also, as you can see, at the very beginning, it did not look like the hypergeometric distribution, right? When we only had 5 data points, but as we added more and more into it, it became closer and closer to what we were expecting. So this is the consequence of what we call the law of large numbers, that the more you do the experiment, the more inputs you get, the closer and closer you are going to come to the true distribution or to the truth. So now we've seen how simulated data is going to form that distribution. So now let's try our own data. Okay, so we only have, so the difference is we were doing it on what eventually became a data set with 2,000 elements, right? But we only have 141 total. Okay, so we're going to do something similar in that we're going to add those data points 5 at a time, and then we're going to construct the histogram with data that's becoming larger and larger. So here, that's where we're going to see that here. Okay, so now, so like I said, this is now our actual data. So I'm taking this from where I placed the actual data. Okay, so let's see. Okay, so we can see there. So as you can see here, it doesn't really look like the final hypergeometric distribution, right? I mean, by the look, just by the looks of it, it doesn't look like that hypergeometric distribution. In the first place, we do have a few 6s and 7s for the hypergeometric distribution that we simulated, but that was over 2,000 data points, that over the course of 2,000 data points, whereas here we only have 141. And the probability of getting a 7 is actually less than 1%. So it's very possible for us to not get a single 7. or even a single 6 in 141 trials. In fact, we can try to look at several histograms of simulated data uh, from a lot of data points and then from only 141 data points in order to help us understand why we have this, we're looking at this distribution of data. Okay, so let's consider this. If we generate data from a hypergeometric distribution, a large number, like 100,000, right? This is 100,000 data points from the same hypergeometric distribution. And we do that 9 times. Each time we're going to plot the histogram. So let's see what we get. So this is what we get. And as you can see, they are very similar to each other. Okay? You can hardly tell them apart. Okay? So all of them look similar to each other, and that is because we are generating these from a large data set, 100,000 data points each time. Now, what if we reduce it to only 141 data points, which is exactly the number of data points that we actually have? So this time, I'm going to do the same, but this time I'm going to generate it from using only 141 data points each time. So, and I'm only going to do it for 8, okay, for 8 times instead of 9. Okay. Okay, so here's what we get. And what do we notice? We notice that they look different, right? So we notice that they look different. Some of them have 7s. So as you can see here, this one has a 7. This one does not. It has some 6s. This one is similar to ours in that it only has a 5 and no 6s and no 7s. So they look very different. They look markedly different from each other, right? And now let's add our own data set to this. This is our own data set. And now that's the 9th data set. And if you're looking at all of these data sets, it's really hard to tell that they are, it's really hard to point out which of them is the odd man out, right? So that's another thing that I want to point out. So it's very different to single out this 9th distribution that we have here, which is our actual data, compared to the rest, which are simulated data. So just by looking at this graphic, there's no way for us to tell if our data, which is here in the 9th panel, is coming from a hypergeometric distribution. Okay? So we will need to make use of a statistical test for that. So let me turn us back to... So here's the Excel file where I got the data. So here are your contributed data points. So all the way down here, those are the contributed data points that I've recorded. Okay, and this is just tallying them up. So out of the data that we've recorded, 5 of them were 0 land hands, 11 of them were 1 land hands, none of them were 6 land or 7 land hands. Okay, so the total number of data points is 141, like I said. So we can conduct a chi-square test, and what a chi-square test does is it compares the actual frequency here to what we expect if the distribution is coming from the one that we anticipate, which is a hypergeometric. So as you can see here, if this data is coming from a hypergeometric with the given parameters, then we expect 3 0 land hands out of 141. So we got 5, but we were expecting 3. And we expect about 17 1 land hands. So we got 11 for that. So and so on and so forth. Okay, so these, of course, are expectations. The further away our actual frequencies are to these expectations, then the more evidence we have that our data is not coming from the intended or the expected distribution. So we can find an actual measure for that by doing the chi-square test. And this is the result of the chi-square test. This is the p-value of a chi-square test when we feed these data into the test. So how do we interpret this value? So if this value is small, and by that we mean typically smaller than 0.05 is a typical standard. So if that value is smaller than 0.05, then that means that we do have sufficient evidence to claim that our data does not abide by the distribution that we're expecting. That is, our data is not hypergeometric. We can be confident to say that that's the case. However, if the p-value is greater than 0.05, then it means that we lack sufficient evidence to claim that our data does not come from a hypergeometric. Note that the wording for that statement is precise, right? So it does not mean to say that we are definitively saying that our data is coming from a hypergeometric. No, but we are claiming, if the p-value here is greater than 0.05, which is the case, that there is not enough evidence based on what we've gathered for us to claim that the data does not come from a hypergeometric distribution. And so it's another way of saying that in as far as the data that we have is concerned, it looks hypergeometric. So that's what it means if the p-value is greater than 0.05. And as we can see, the p-value is indeed greater than 0.05. It's 0.288. So what about if we feed simulated data to our chi-square test? Okay, so we expect that if we feed simulated data to our chi-square test, then we should also be unable to find sufficient evidence that our data is coming from something other than hypergeometric. Right? So let's try to do that. So in order for us to do that, let us get this. That's our code for generating hypergeometric. So we're going to generate hypergeometric distribution, 141 of them, and put it in a variable, let's say A1. Then let's do that again, A2. Then let's do that again, A3. So I'm going to export these as CSV files. Right? And then we are going to use them to conduct our test. Alright, so I have exported those three simulated data sets, and I have here a blank sheet where we can just input these data sets. So I have them here. This is A1, A2, and A3. So these are simulated data. So what we expect is if we use this, since we know that these are coming from a hypergeometric, right? So if we place this here, then the test should not be able to detect that these data differ from a hypergeometric. So let's see. So I'm going to paste it here. And so as you can see, our p-value is still greater than 0.05. So for A1, we would still make the same decision. We would fail to reject our null hypothesis that the data is coming from a hypergeometric. Right, now let's try the second one. So still, p-value is greater than 0.05. And how about the last one? So still, p-value is greater than 0.05. So you can do this over and over again, and there will be some instances where the p-value will become less than 0.05, but it will be rare. Okay, so it will be rare. And so that shows you that indeed, if you're using simulated data from a hypergeometric and you use a chi-square test to it, the test will show that the data is coming from a hypergeometric, that there's no evidence, the test will show that there's no evidence to indicate that the data is coming from a distribution other than hypergeometric. And so now let's consider what happens if the shuffler was somehow cheating people, right? If the shuffler was somehow cheating people, would we able to detect it? Would we be able to detect it? Would the chi-square test be able to detect it? Well, of course, there are a lot of possible ways by which a computer program can be altered, right? So we cannot really consider all those possibilities. So I'm going to consider something that is only a very slight change or a slight change to the actual distribution. So what is this slight change? So suppose that the shuffler is made so that about 2.5% of the chances of you getting a 0 land hand or a 1 land hand or a 6 or 7 land hand is higher than normal, or that is higher than what is expected. So this is what this code does. So what this code does is it increases the chances of you getting a 0 land hand or a 1 or a 6 or a 7 land hand. Okay, but it increases it only slightly. So as you can see here, the chances of you getting a 0 land hand is increased by about 2.5%. So same thing for the others, only about 2.5%. So if we use this, I'm going to plug this function in. Okay, what would the data look like? Okay, so let's see. Let's make a histogram of. Let's first look at a lot of data points. Okay, let's look at. Is this 10,000? So let's make it. Yeah, 10,000 data points should be enough. Okay, let's make the density. Oops, let me close this. Okay, so this is what it looks like. So you can see the difference, right? Even just looking here, you can see that this column for 7 is higher than it should be in a hypergeometric, right? So is 6, right? Now, how about if you only have 141 data points? So if you only have 141 data points, you still see sort of a difference because we are seeing 7s and 6s, right? More often than we did when we were generating from a hypergeometric. But of course, these are just visuals. Again, you cannot say definitively for sure just by looking at the visual. You have to test. So let's export this. Let's export again. Let's put this in different variables, B1. Each of them will only have 141 data points. Right. Okay, and then I will export these. I'll export these, and then we will feed these to our Excel file. All right, so I have shaded, I've exported them here. So this is B1, this is B2, this is B3, and I shaded them so that they could differentiate them from the earlier ones that were coming from the actual distribution. So now let's do the test, right? So I'm going to copy this. I'm going to paste it here. Let's see what happens. And as you can see, the p-value is very, very small. It's 7.3 times 10 to the negative 43. Right? And you can see that because we were only expecting one. We were only expecting 1 to 2 elements coming from the 6 land hands, but we actually had 7 of them. And we were only expecting. We weren't really expecting any hands coming from a 7-land hand. I mean, we're not expecting anything. Uh, we were not expecting getting a 7-land hand, and yet we got 5 7-land hands. So that is very far from a hypergeometric distribution. And that's why you can see here that the p-value is very small. And so we can definitely say here that there's something wrong. And we know for a fact that there is something wrong because, as you saw, we did fudge this shuffler, right? We included a cheat in this shuffler where it would produce more 0 and 1 land hands and more 6 and 7 land hands than would a typical hypergeometric distribution. Let's try the other two. So these are also uh, coming from the bad distribution. And as you can see, it's still very small, right? It's still significantly detectable, that difference from a hypergeometric. And so as you can see here, if you're looking at just the figure, it's difficult to tell because the general shape, at least for some of these, are the same. Here it's not, and 7 is really going up there. But for the others, like for this one, the shape is quite similar, right? Or it bears some similarity at least, but the test does not lie. Or at least it's not supposed to lie. It can be 95% confident, as we say, depending on the pre-specified level of confidence that you specified for the test. Okay, so what this shows is that if the shuffler was fudged in the way that we fudged it, that would show. And note that the way that we fudged it was not very obvious, right? We only changed a little bit of the probabilities, but that was enough for it to be detected by the test. And so what I'm trying to get at here is that, of course, that's not the only way to fudge the shuffle. That's not the only way to mess with the shuffler, right? There are 1,001 ways to do that. But really, it's quite detectable. If you do mess with the shuffler so that it does not produce a hypergeometric with enough data, you would be able to show that quite easily, that the data is not coming from a hypergeometric. So what are the takeaways that we can get from what we just did here? So first, we were not able to find evidence that the shuffler's behavior is different from what is expected. We were expecting that the shuffler behaves as a hypergeometric in as far as the number of lands in the opening hand is concerned, and based on the results that we got, it does seem to behave that way. However, we only considered one specific context. Of course, you can do more of these experiments, varying the size of the deck. So maybe change the size of the deck from 60 to 70, and then try everything again and check if it's still hypergeometric. Of course, the distribution will still be hypergeometric, but with different probabilities. Okay, so you can change the number of lands. You can have still a 60 land deck, but 60 card deck, but you can change the number of lands to 20 or something like that. You can even change the number of cards drawn. Okay, so instead of just observing the opening hand, you can observe the up to the 10th card drawn, for example, and factor that in. So there are a limitless number of contexts, and there's really no way to test all of them, practically speaking. So, but then the idea is to somehow show that there is strong evidence, right? So it's not just a matter of trying to find one instance where it doesn't work, but be able to replicate that instance, right? So that we can be certain that indeed something is wrong with the shuffler. But in as far as this experiment is concerned, we have found absolutely no evidence that the shuffler is behaving different from what is expected. And that concludes the second episode of the Death by Variance video articles. So I hope you enjoyed that. But before we call it a night, we do have one 1000 gem pack to give away. And we are going to give it away to one of the people who graciously contributed data to our article. And so this is a list of the names of the people who did contribute their data. So we are going to pick one lucky winner at random from these people. So how am I going to do that? Well, I'm just going to generate a random number, okay? And the person who gets the highest number wins, right? So it's simple as that. We're going to generate the number from a uniform distribution. So that means that any number from 0 to 1 have an equal chance of getting represented. So let's do that. Excel. Okay. Copy. So these are the numbers we got. Okay, so these are the final numbers. We had to copy them and paste them as values. Okay, so now these are fixed already. This can no longer change. And so it's time to pick our winner, whoever got the highest value. Let me sort. Where is that sort? Custom sorts. We'll sort by B from largest to smallest. And our winner is Mike Gordon. So Mike Gordon wins a 1000 gem pack. I will PM you the code. And so thank you everyone for watching, and I'll see you again next time.